Alright guys, so now we're going to be talking about the conservation of linear momentum and impulse for a system of particles. So just like in the conservation of energy, in this case momentum has to be conserved. So it's only transferred from one system or from one particle to another. So when do I apply this system or this method? It is whenever the particles collide or interact. And this is the basis for the whole lecture that we're going to do later on collisions. So for this conservation of linear momentum and impulse, we have once again two types of forces. Non-impulsive forces, so those forces that do not cause or have negligible impulses, such like the weight of a body or the force imparted by a slightly deformed spring having a really small stiffness. While the impulsive forces are those which are very large and act for a very short period of time, producing a significant change in momentum. So if your particle is moving one direction and then gets hit or interacts with a certain force that changes its trajectory, changes its direction of motion, changes its momentum, that will be an impulsive force. So any forces that strikes the body against one another, that will be an impulsive force. So notice the equation right there that we have. It's given here, and it is the sum of masses times their velocity once, or their momentum at state 1. It's equal to the sum of momentums at state 2. So we gotta sum every mass and every velocity. So we have, for example, here, notice particle A with a certain mass A and a velocity A1. So a momentum is given here, mass times velocity, state 1. And we have a particle B right here that has its own mass B, and its own velocity velocity B1. And we can see that they're going against each other. They're going to definitely collide. And in this case, in this situation, sometimes they bounce back, sometimes they stick together. We'll see that later on in the collision problems. But for now, we see that they stick together. So whenever we want to find the momentum at state 1, we will sum the momentum. So the momentum of velocity A, or particle A, plus the momentum of velocity B should equals to the momentum seen by both particles now that they're stuck together, sharing a common velocity v2. So notice in this case you can say that probably velocity A was bigger, or definitely also high momentum because it has a higher mass, just by comparing on this just by their size. So let's say they stick together, they move now as one body, so their masses are combined. So and that means that they will be sharing one velocity final. And once again, the momentum, if you add up these values, they should be the same, right? Because we're doing the conservation of momentum. So that's pretty much how they work, right? Similar to the conservation of energy. So let's do a couple problems on this ones to see how this works. We have here this system right here. We have these freight cars that are going to collide against each other. So we have freight car A and B. The mass of the first one, of A, is 200 million grams, and the mass of the car B, it's 15 million grams for freight B. They're asking us to determine the velocity of A after the collisions if the cars collide and rebound, such that B moves to the right with a speed of 2 meters per second. If A and B are in contact for 0.5 seconds, find the average impulsive force which acts between them. All right, so these problems are also pretty straightforward. They're not complicated at all. They're pretty easy. So the mass of A, it's equals to 20 million grams, or that is equivalent to 20,000 kilograms. Therefore, the mass of B, it's equivalent to 15,000 kilograms, or 20 metric tons, and 15 metric tons. Right? VA1, it's equals to our velocity of A at state 1. It's 3 meters per second. We're going to say it to the right. Remember, these are vectors. Velocity of B at state 1, that is equals to negative 1.5 meters per second. Right? Because noise is going to the left, so we're going to do the vector. So we can write it as 3 like I and like that, right? Because they're vectors. And then we also given that after rebound, the velocity of B2 is now moving to the right at a speed of 2 meters per second. So notice it gains some speed, BV gains some speed, because yes, has less mass, so all the momentum that car A has as it collides, a lot of it is transferred into car B, and it moves to the right at a higher speed than it initially had. Meaning that if B gains speed, then more than likely A decrease a lot in its momentum. It decreases its speed, because we cannot really change masses in this kind of situation. So the only thing changing is the velocities. So this one kind of already gives us an insight as to what our value should be. So if we get the velocity of A being bigger than it originally was, we get something wrong, because we cannot add momentum, right? Just like energy, you cannot create momentum. It's conserved. So what it already has, if it gains speed, the other one has to decrease. In this case, we know B is sped up, so A has to decrease in energy. So let's draw, what happened. Kind of like these are our momentum diagrams. So then we have car A. It's moving at a speed VA1, right? VA1 plus we have then car V, or trade car B. So this is mass B moving at a certain B1, certain velocity 1. And then after collision, we have both cars still, I think they should be going in the same direction. Could be that they're bouncing back and going opposite directions. We'll find that out, but we'll assume that it is going to the right. If we get a negative value, it means that our car A is going in the opposite direction. But at least for now, we can assume it's going to the right. So mass B, we know that this is going at a speed B2. So yeah, these ones, they do bounce back. So using the equation for conservation of energy, we're gonna write here the following. So we have mass of A, VA1, plus mass of B, BB1. It's equals to mass of A, VA2, plus mass of B, VB2. Notice for this equation, we do know pretty much everything. We know the masses, we know velocity initial A, velocity initial B, velocity final B, and the only thing that we're looking is for velocity A2. So if you plug and chug and you rearrange, right, once again, there's no too much algebra on this. You cannot cancel the masses because they're different. But once again, it's just rearranging. You just have to move everything to the side, divide everything by mass of A. And because of time, I'm just going to give you the solution. But VA is calculated to be 0.375 meters per second, in the I direction. Meaning that, yes, it is moving towards the right. So we are good in our definition. So that's it for that one. And then to figure out the impulse between the cars as they collide, we're going to use the equation for impulse and momentum. So we have, you can do from A to B or B to A. They're going to share the same impulse, right? Because they're both colliding. So let's do the one for B. So we have the mass of B times the velocity of B1 plus the sum of forces, right, integrated from T1 to T2 equals to the mass of B times BV2. Once again, we already know their values, so we know everything here. So this will be, once again, mass B, velocity B1, plus the average force, that's on the impact force. As they collide, they're going to impact each other. So this is the only average force times the 0.5 seconds that they are in contact is equals to mass of B times VV2. If you arrange to solve for the force average, you'll get that this is approximately 105 kilonewtons. Notice that is a lot of force. I put kilonewtons, so that's 105,000 newtons. So again, that's from rearranging the equation right here.